Welcome, class. Today we are going to begin Chapter 7. In this chapter, we're going to be talking about chemical reactions. We're going to first look at how we write out chemical reactions and some of the things that go along with writing out chemical reactions. And then in the next part of the chapter, we're going to look at a couple of different specific types of reaction. And these include precipitation or solid forming reactions and oxidation reduction reactions. Specifically, combustion we'll look at in a little in detail, which is a type of oxidation reduction reaction. So before we jump into looking at those specific types of reactions, first of all, we need to look at chemical reactions in general. So remember, we've talked about chemical reactions a little bit earlier in the course when we looked at chemical changes, right? So remember, chemical reaction is just another term we use to describe a chemical change, right? So we had physical changes and chemical changes, and now we're going to look specifically at these chemical changes. So remember, when we talked about a chemical change, it was a type of change in which the matter that we started with, the type of matter that we started with, changed into some other type or types of matter, right? So we had to change the composition, right, during that chemical change. So the transformation of one or more substances into different substances, right? That's what we're looking at here. Now, how do we know, or how can we observe qualitatively that a chemical reaction may be taking place? Well, there are several sort of visual signs or signs that we can measure that'll tell us that perhaps a chemical reaction is taking place. Among those are a color change. So if a material or a solution or the reaction changes color during the chemical change or during the change, right, that's often a telltale sign that we're forming some new type of matter. The formation of a solid, right, is a good indicator. We'll look at this a little more specifically when we look at precipitation reactions. Formation of a gas, right? So similar to formation of a solid, but in this case we're forming a gas. The emission of light or giving off of light can often be a clue that something is happening, right? The emission of energy. And go along with that, the emission or the absorption of heat. Again, this falls under the general category of energy changes that often accompany the chemical changes that we're talking about. Now, we should keep in mind that these are indicators, right? These do not guarantee or they're not proof of a chemical reaction. The only way that we can do that is to analyze the material that's left at the end to see if it's actually changed. Now, for example, we could be fooled when, for example, we boil water, right? When we boil water, right, a gas is produced, right? But there is no chemical change going on, right? It is simply a physical change. Remember, all changes of state are simply physical because the matter is still the same, right? When that water boils, you've just changed it from liquid water into gaseous water, but the composition is still the same. Now, goes along with that, right? Heat is given off. So heat is given off, or you sense heat being given off when we boil water. But again, this is, part of the physical change that's going on, right? No chemical change has occurred. So we have to be a little bit careful when we look at this and understand a little bit more about what's going on. So when we write out a chemical change, we do it in the form of what's called a chemical equation, right? So I'm sure most of you are familiar with the general format of a chemical equation, which we show here, right? And so let's talk about some of the components of a chemical equation. So how do we know, how can we, when we see this written out, what tells us that a chemical change is occurring? Well, first of all, we're rearranging atoms, right? Atoms are combining with other atoms to form compounds, or new molecules are forming, or the original molecules are decomposing into different molecules. So the bottom line is the materials we have at the end are different than the materials we had at the beginning. Now, the materials that we start with, right, are the reactants, right? So these are our reactants here. And the substances on the right side that we end up with are called the products. So we read this as in the reactants react to form the products, right? And we move from left to right. Now, last thing that I'll point out here is that we should specify the state of matter that the materials are in. So you'll notice that each reactant and product has a symbol in parentheses that's telling us what state the reactant or the product is in. So, for example, in this reaction, this G here in all four spots is indicating that everything is in the form of a gas. So anytime we write out a chemical equation, we should put in parentheses what state of matter that it's in. Now, we must balance a chemical equation. So, what do I mean? When we write out a chemical equation, it must be balanced. So, we'll have atom balance is the key, right? So we can't just write that one thing forms another thing, right? We have to show conservation of matter. Right? So we know conservation of matter, right, is taking place, right? The law of conservation of matter. We have to show that when we write out a chemical equation. And the way that we do that is that we show atom balance, which essentially means we have the same number of each element on both sides of the equation. So if we look at this reaction between CH4 and oxygen, forming carbon dioxide and water, we'll note that, for example, on the reactant side, we have 2 atoms of oxygen coming from one of our one O2 molecule here. But on the product side, we've generated 3 atoms of oxygen, right? 2 from the molecule of CO2 and 1 from the molecule of water. Now, this is of course impossible, right? We can't start with 2 oxygen atoms and all of a sudden have 3, right? In a chemical reaction, atoms don't change what they are. So we have to balance this. Now, the way we balance is to use coefficients. So these are numbers that we place in front of all of the reactants and products to denote how many molecules or atoms are reacting, right? So it may not just be one thing reacting with one thing, right? So these coefficients are going to tell me how many molecules of each material are reacting. So how do we approach this? Well, we look at what we have, right? And we try to balance it in such a way that we can do it a little bit systematically. Now, I will tell you there is no set way that we balance an equation, right? There's no process that is always used, right? Different people visualize these things differently, and so we use different approaches. But the bottom line is we have to end up with a balanced equation at the end. So let's walk through this one in a way that we might approach it. So a couple of hints. It's often good to balance things that appear in one place on the reactant and one place on the product side first. So for example, if I look at the carbon, On the reactant side, I have one carbon right here. On the product side, I have one carbon. So at this point, the carbon is balanced. So let's look at something else, right? And look at the hydrogen. So on this side, we have 4 hydrogen atoms. And on this side, we have only 2 from the water. Well, how can we balance that? Well, this is where this 2 comes from. So we use a coefficient of 2 here to get me to 4 hydrogen. So what I'm saying now is I formed 2 water molecules, which in total have 2 times 2 are 4 hydrogen atoms. So by putting that coefficient of 2 now, I've balanced the hydrogens. So I have 4 atoms over on the reactant side, 4 atoms on the product side. And lastly, I'm going to look at the oxygen, because oxygen appears in 3 different spots. So we'll save it to the end. Makes us have to do a little bit less backtracking at the end of the process. So we see, to start out, we have 2 oxygen atoms on the reactant side from our O2. If we look on the product side, we have 2 oxygen atoms from the 1 CO2, and now we have 2 oxygen atoms from the 2 waters. So we have a total of 4 oxygen atoms on the product side. Now, we had 2 on the reactant side, so again, how can we make this match? Well, in this case, if we put a 2 in front of the O2, now we've balanced, right? Now we have 4 oxygen atoms on the reactant side to go along with our 4 oxygen atoms on the product side. And so by putting these coefficients in front of the oxygen and the water, we've balanced the equation so that we have 1 carbon atom on each side, we have 4 hydrogen atoms on each side, and we have 4 oxygen atoms on each side. And our balanced chemical reaction is 1 CH4 reacts with 2 O2s to give 1 CO2 and 2 waters. And that's our balanced chemical equation. And the one thing that I will point out here is that we only ever add coefficients, right? We do not change subscripts in order to balance an equation, because if we do that, that changes what the substances are, right? And we already know or have what the chemicals that are involved, what the reactants and the products are, so we never ever change the subscripts, only coefficients in process of balancing an equation. Okay, now let's do a little practice on balancing chemical equations. So I mentioned earlier that when we write out a chemical equation, we always show the states of matter. So before we do these, I want to show you what the possibilities that we could have here. So of course we have our 3 normal states of matter, right? We could have an S for solid here, we could write an L for liquid, and a G for gas. But we also have a 4th symbol that we might see, and that is an AQ. And that means aqueous, right? And we'll see that a lot as we go through some of the reactions that we look at. And what this means is that we have an aqueous solution, or in other words, the material is dissolved in water. And so we'll get to that more specifically in the next section, but so you know what you're looking at when you see these things. So let's look at these equations and start balancing them. So some equations are pretty straightforward, some are a little harder. So let's try this first one. So I'm going to start with the chromium. And so we have our CR. We have 2 CRs on the reactant side, only 1 on the product. So I'm going to put a 2 here to balance the CR to start with. Okay, so now how about the oxygen? Well, I have 3 oxygen over here on the reactant side, but only 2 on the product. So a couple of things here, right? So I have 2 and 3. There's no easy way to balance this, so I could put 1.5 here, and that would eventually, we could get to the right answer, because we can't have fractions here, but that we could use that as a placeholder. Now the other way to think about this is that if I have 2 here and 3 over here, what is the lowest common number that 2 and 3 both go into? And of course that's 6, right? And so in order to get 6 oxygens over here, I would need a 3. And to get 6 oxygens over here, I would need a 2. So we have 2 times 3 is 6, 3 times 2 is 6. Now, of course, by doing that, it now changed the chromium. So now I have 4 chromiums. And so I can go back and change this 2 to a 4. So now my chromium and my oxygen are balanced. So what about the carbon? So I have 1 carbon on the reactant side, and now with this 3 here, I have 3 carbons on the product side. So that's easy enough to balance. I can put a 3 here. And now we have our balanced chemical equation that we would write out. And we would write out 2Cr2O3. Now, I'm leaving out the states of matter just to show you the balanced equation, but of course, they should always be included when you actually write out the chemical equation. So we've added our coefficients, and now we have a balanced equation with 4 chromiums on each side, 6 oxygens on each side, and 3 carbons on each side. Okay, let's try another one. So in this case, let's say we have 4 carbons on this side, and on this side we have 1 carbon. So I'm going to put a 4 here to balance that out. I'm going to move to the hydrogens. I have 10 here, I have 2 here, so I can put a 5 here to balance that out. So now I have 4 carbons on each side, 10 hydrogens on each side. Let's go to the oxygens. So of course here I have 2 for the 102. On the product side I have 4 times 2 are 8, 5 times 1 equals 5. I have 13 oxygens. Now of course I have 13 and 2, and of course no easy way to balance that at this point. I would need 6.5 to get there. Now we didn't do it above, but this time I'm going to use the 6.5 as a placeholder here. Now, we can't leave it this way, but we can now look to see that, of course, it is balanced here with 4 carbons, 10 oxygen, 10 hydrogens, and 13 oxygens on both sides. Now, the easy way to get rid of this, to put it in proper form with whole numbers, is to multiply everything by 2, right? To turn this 6.5 into a whole number. But we have to do it to everything. So when I do that, this becomes 2, this becomes 13, this becomes 8, and this becomes 10. And so my balanced equation becomes 2C4H10 plus 13O2 goes to 8CO2 plus 10 water. And that's my balanced equation. Let's try one more here. So we have lead acetate plus potassium iodide goes to lead iodide plus potassium acetate. Now, I did in one with here with a polyatomic ion, right? This is one of the polyatomic ions we're going to eventually memorize, acetate. Now, one thing I want to point out here is, as long as the polyatomic ion is showing on both sides, so it hasn't decomposed, then we can balance it as a group, and that makes balancing it a lot easier, right? So we can just treat it as if we were balancing an element. We're going to balance acetates. So if I look here, I have 1 lead on the reactant, 1 lead on the product, okay? I have 2 acetates, so the 2 here tells me I have 2 of these, and on this side I only have 1, okay? So how are we going to balance that? Well, let's put a 2 here. So if I go to the next one, I go to potassium, I have 1 here, I have 2 here, so we're going to balance that with a 2 here. So So lastly, the iodine, I have 2 I's here, and I have 2 I's here. So now we should all be balanced. 1 lead on each side, 2 acetates on each side, 2 potassiums, 2 iodides, and we end up with our balanced equation of PbC2H3O32 plus 2Ki goes to PbI2 plus 2 potassium acetates. And lastly, I'll give you an example of one where they don't give you the equation, but they give you a description of the equation. So here we want to write a balanced equation for the reaction of hydromonochloride gas, oxygen gas, to produce liquid water and chlorine gas. So let's write it out first. So we have hydrogen monochloride, so that's HCl, and it's a gas, plus O2 gas, right? Remember, oxygen gas has the formula of O2. It's a diatomic element. Goes to liquid water plus Cl2 gas, right? Remember, chlorine, right? Again, exists as one of those diatomic molecules. So it's important that we start to remember those and to learn those. So now that we've written it out, we can now balance it. So if we look at hydrogen, we have 1 on the reactant side, 2 on the product. So we're going to put a 2 here. I have 2 Cl now and 2 Cl. Okay, good. I have 2 O2s and 1 O on this side. Okay, so I can balance that by putting a 2 here. So now this, I have to go back and check because now I have 4 hydrogens over here, but only 2 over here. So I have to make this a 4 instead. So I have 4 HCl. Now this changes that I have 4 chlorines, so I have to go and add a 2 here. So my balanced equation becomes 4 HCl plus O2 goes to 2 waters and 2 Cl2s. Give me 4 hydrogens on each side, 4 chlorines on each side, and 2 oxygens on each side. Okay, so that's just a few examples of balancing equations. Again, like any skill, we need to practice it, so the more practice you can do, the better off you're going to be.